Okay, so on number 16 we have a hollow sphere that looks surprisingly like a tennis ball, and you're given that the moment of inertia is 2/3 mr squared, and you have the mass of the tennis ball, 24 grams. Might want to work a little magic with that. And you've got a radius of 3 centimeters. Might want to work a little magic with that. And with that information, you've got the radius, you've got the mass. So at this point, you can calculate I. But being the brilliant physics students that you are, you realize to get that angular momentum, you got to have L equals I omega. So this will get you I, but you don't know omega. But because I was a jerk when I made up the problem, I gave you 30 revolutions per minute. Well, that's not bad, because we know that one revolution is 2 pi radians, and 1 minute is the same as 60 seconds. So going old school, if you do a little bit of cancellation, you can realize, wow, that's 30 times 2. That gets me 60. Even without a calculator, I can figure out that that cancels that out. Everything goes away. And it's an odd deal, but you get pi radians per second. So at this point, you know omega. So next on the hit parade, value of your angular momentum. So your answer to number 16 should be something around 10 to the minus 5th, if all goes well. Now, when you get down to number 17, and along comes the bug. So here's the ball, tennis ball, spinning, and the bug comes along, and it lands on the equator. So at this point, it becomes a conservation of momentum problem. And again, all of these start the same way. But what's going to be important is that you realize that it lands on the outside of the spinning ball. So knowing that, all right, at this point we have two things. We have the momentum, angular momentum of the ball, plus the angular momentum of the bug initially is going to equal the new L of the ball plus the new L of the bug. Now, the bug wasn't part of the system initially. That drops out. So, looky here, sports fans. This is I of the ball times omega of the ball. Well, guess what? This side over here is your answer to number 16. Don't recalculate it. You already have it. Now, over here, because the ball is spinning and the bug is part of that system, it's like two carts that hook up and move off together, the California roll. So because the ball and the bug are spinning at the same rate, you can go, oh, this is going to be the eye of the ball, kind of a little witchcraft thing. You go, oh, that's the eye of the bug times omega prime. So what you're searching for is omega prime. Now, if you recall, this initial value over here was 3.14 radians per second. So if you think this through and you go, wow, I'm going to increase that moment of inertia, so to make all things balance out in the world, that new omega has to be smaller than 3.14. So if you saved that separately, you already have the eye of the ball from number 16. You got to calculate the eye of the bug. So with the eye of the bug, you're just going to use mr squared, but make sure that you use the radius of the ball, because that bug is sitting on the outside of that spinning tennis ball. So you're going to know this whole thing. That's your answer to number 16. You already know the eye of the ball. You're going to calculate the eye of the bug, and you're going to solve for omega. So if all goes well, your answer to number 17 should be around 223 radians per second. And there you have it, kids.